Welcome to another episode. Before we begin, tell me something in the comments. Where in the world are you listening from, and what time is it there right now? It's always fascinating to imagine this small circle of light scattered across time zones and continents, quietly listening together to the same story. If you haven't already, remember to subscribe, so you can drift with us through more journeys like this one. Now, settle in. The fireplace crackles softly in the background, and tonight, we're going to talk about something that, for a long time, was believed to be the very definition of silence. A place where no sound, no light, no signal could ever escape. A place where even time seems to stop. A black hole, and yet, as it turns out, even the blackest void in the universe is not entirely mute. It whispers, it evaporates, it glows, faintly, quietly, through a process that Stephen Hawking revealed to the world in 1974, a discovery so paradoxical that even he didn't believe it at first. This is the story of that whisper, Hawking radiation, and what it tells us about the most secret places in the cosmos. Black holes are born from death, specifically from the death of stars. When a massive star burns through its nuclear fuel, gravity wins. The outward pressure that once resisted collapse disappears, and the star implodes under its own weight. In the final moments, the core shrinks until its density defies imagination. Matter crushed into a single point, a singularity surrounded by a boundary called the event horizon. Beyond that horizon, escape becomes impossible. Not for light, not for information, not for hope. That was the classical picture, at least, the one Einstein's general relativity gave us, and for decades, that was where the story seemed to end. A black hole was a perfect absorber, a cosmic prison, an object defined by its silence. It was not supposed to have a temperature, not supposed to emit anything. As far as anyone could tell, it was the universe's ultimate trash bin. Whatever fell in, stayed in forever. Einstein himself never liked black holes. He thought nature would find a way to avoid such absurd extremes. In 1916, just months after Einstein published his field equations of general relativity, a German physicist named Karl Schwarzschild sent him a letter from the Russian front where he was serving during World War I. In it was a mathematical solution, the first exact one to Einstein's new equations, describing the gravitational field around a spherical mass. That solution contained something strange, a boundary at which the equations broke down completely. Einstein acknowledged the math, but brushed it off. He assumed it was merely a mathematical artifact, not something that could actually exist in the physical universe. For decades, so did everyone else. It wasn't until the 1960s, when a generation of physicists armed with new telescopes began finding intense X-ray sources in the sky, that the idea of a real black hole began to harden. Objects like Cygnus X1, discovered in 1964, radiated energy in ways that could only be explained by matter falling into something incredibly compact. More compact than a neutron star. It was as if the universe had hidden drains, scattered across its fabric, swallowing whatever strayed too close. John Wheeler, the American physicist who coined the term black hole in 1967, described them as the most perfect objects in the universe. Perfect because, according to the mathematics, they could be described entirely by just three numbers: mass, charge, and spin. Nothing else mattered. Whatever fell in, a star, a planet, a poet, would be erased. All its details, all its complexity would vanish behind the horizon. What came out, if anything, would be a smooth, featureless gravitational field. That elegant simplicity, however, was deeply unsettling. If the laws of physics are supposed to be reversible, meaning that information about a system's past can, in principle, be recovered, then a black hole seemed to break that rule. Information that crossed the event horizon was gone for good, and in physics, gone for good is not a comforting phrase. It's like saying the law of conservation of energy only applies most of the time. Still, no one expected the solution to come from quantum mechanics, and certainly not from Stephen Hawking, a young cosmologist at Cambridge, confined to a wheelchair by motor neuron disease, whose body was failing but whose mind was moving at light speed. In the early 1970s, Jacob Bekenstein, a graduate student in Princeton, had made a radical suggestion. He proposed that black holes should have entropy. Entropy, that measure of disorder or missing information, was known from thermodynamics to increase in all natural processes. It was the arrow of time. And if black holes erased information, they seemed to break that law too. Bekenstein argued that perhaps the surface area of a black hole's event horizon was proportional to its entropy. A larger horizon meant more hidden information. To most physicists, this was metaphysical nonsense. Hawking himself called it absurd. He decided to prove Bekenstein wrong by applying the machinery of quantum field theory near the event horizon. What he found instead was one of the most shocking results in 20th century physics. According to quantum theory, empty space is not truly empty. Even the vacuum teems with what are called virtual particles, tiny transient fluctuations that pop in and out of existence, borrowing energy from the vacuum for the briefest instant before annihilating again. Normally, these pairs, a particle and its antiparticle, cancel out perfectly, leaving space seemingly empty. But near the event horizon, the balance is disturbed. Imagine a pair forming just at the edge. One particle falls inward, trapped forever. The other escapes to infinity. From the outside, it looks as if the black hole has emitted a particle, radiation coming from its surface. Of course, the black hole loses a tiny bit of its mass in the process, because energy has left the system. And if you let this process run for long enough, the black hole will gradually lose mass, shrink, and eventually evaporate. Hawking calculated that this radiation would have a precise thermal spectrum, as if the black hole had a temperature. The larger the black hole, the colder it is. A stellar mass black hole might have a temperature of only about 60 nanokelvin, colder than the cosmic microwave background that fills space at 2.7 Kelvin. Meaning it actually absorbs more energy from the universe than it emits. Only when the universe cools below that temperature, trillions of years from now, will such a black hole start to evaporate in earnest. But for smaller black holes, like hypothetical ones from the early universe, the temperature rises dramatically. A black hole the mass of a mountain would glow at thousands of degrees, evaporating in a burst of gamma rays in a fraction of a second. The idea was astonishing. It unified thermodynamics, relativity, and quantum mechanics in a single breath. And it suggested something deeply poetic, that even the darkest places in the universe are not immune to time. Even they must fade. When Hawking first presented the result, colleagues thought he'd made an algebraic mistake. The notion that a black hole could emit radiation seemed to contradict everything general relativity stood for. John Taylor, a fellow Cambridge physicist, even bet against him, declaring the radiation would never be found. Years later, when the theory held up under scrutiny, Hawking received the most satisfying apology in scientific history, a framed certificate admitting defeat. Still, the implications were troubling. If black holes evaporate completely, what happens to all the information that fell in? Does it vanish with them, leaving the universe with less information than before? If so, quantum mechanics itself might need rewriting. The information paradox was born, a puzzle that still hasn't been fully solved 50 years later. But before diving into that philosophical abyss, it's worth pausing to marvel at what Hawking's result meant. For the first time, something resembling temperature could be assigned to a gravitational object. Entropy, once a measure of the disorder of gas molecules in a box, now applied to the surface of a black hole. It meant that even in the emptiest reaches of space, the same principles that govern boiling kettles and melting ice also hold sway. The universe, it seemed, plays by one consistent set of rules, from the kitchen to the event horizon. There's an elegant proportionality in the equations. A black hole's entropy is proportional to the area of its event horizon, not its volume. That's counterintuitive. We're used to thinking that information, or disorder, grows with volume. The more space, the more possibilities. But for black holes, it's the surface that counts. A hint, perhaps, that information itself might be stored on two-dimensional boundaries. That clue would lead, decades later, to the holographic principle. The idea that our entire three-dimensional universe might be a projection of data encoded on a cosmic horizon. It all began with Hawking's whisper of radiation. He himself called it the most beautiful calculation of my life. He worked it out not in a high-tech lab, but sitting at his desk, aided only by pen, paper, and an increasingly uncooperative hand. By the early 1970s, ALS had taken away most of his mobility. He typed slowly, thought faster. The irony of a paralyzed man discovering the slow evaporation of the universe's most powerful objects was not lost on him. In his quiet way, he understood that the black holes and he shared something. Both were losing energy, very slowly, to time. He once said, "Black holes are not eternal prisons. They are more like burning stars, very slow fires that eventually die out." The phrase slow fire captures the haunting essence of Hawking radiation. The process is so subtle that no one has ever directly observed it, yet the math leaves little room for doubt. Every black hole glows faintly, its heat barely above absolute zero, its radiation lost among the cosmic background noise. But it's there, like the faint breath of a giant sleeping in the dark. From a human perspective, the timescales are incomprehensible. A black hole the mass of the Sun would take roughly 10 to the power of 67 years to evaporate. That's a number so vast it makes the current age of the universe, 13.8 billion years, seem microscopic. If you were to compare the two, it's like a blink versus eternity. And yet, somewhere in that unimaginable future, long after every star has burned out, long after the galaxies have drifted apart into darkness, each black hole will emit its last photon, its final whisper of existence, before disappearing completely. Physicists sometimes refer to that final flash as the black hole death cry. It's not an explosion in the ordinary sense, more like the ultimate sigh of a universe reaching equilibrium. No more potential energy, no more gradients, no more imbalance to drive change, just smooth, eternal cold. The end of heat, the end of contrast. Entropy fulfilled. And perhaps that's why Hawking radiation feels more like poetry than physics. It's not merely about particles escaping from gravity's clutches, it's about impermanence, the cosmic version of mortality. Everything that exists, no matter how massive, how eternal seeming, will one day fade into nothing. Even the void itself has a lifespan. In a sense, Hawking's discovery didn't just change our understanding of black holes, it changed our understanding of nothingness. Before 1974, nothing was truly thought to be nothing. Empty space, zero energy, zero possibility. After Hawking, we understood that the vacuum is alive with activity, a restless ocean where existence and non-existence dance continually. Nothingness, it turned out, is full of something. That insight rippled far beyond astrophysics. It influenced quantum cosmology, particle physics, and even philosophy. If space itself can give rise to matter and energy spontaneously, perhaps the universe didn't need a cause to begin. Hawking would later write, "Because there is a law such as gravity, the universe can and will create itself from nothing." A sentence that sounds heretical or profound, depending on how late at night you're listening. But it all began here, with one young physicist daring to ask whether black holes truly keep their secrets. He found that they don't. Not entirely. They whisper. Their edges shimmer faintly with stolen energy, borrowed from the vacuum, paid back with their own mass. It's a whisper so faint that not even our most sensitive telescopes can hear it. And yet, in that whisper lies the bridge between relativity, quantum mechanics, and thermodynamics, the three great pillars of modern physics, meeting for a fleeting moment at the rim of oblivion. Somewhere, billions of light years away, a black hole might be doing it right now, emitting a handful of photons every century, slowly thinning, imperceptibly fading. To us, it's silence. To the universe, it's the sound of balance being restored. And as the glow escapes, it carries a message, though not one written in words, that even the darkest things in existence are not beyond change, that even in the deepest void, something moves, breathes, and finally, lets go. When you picture the mid-1970s, the world of physics was still echoing with the aftershocks of Einstein, relativity had turned 60, quantum mechanics about 50. They had both reshaped our understanding of nature, one describing the grand curvature of spacetime, the other the restless jitter of subatomic uncertainty, and yet they refused to speak the same language. Every attempt to make them coexist ended in contradiction, infinities, or absurdities. And between them stood the most enigmatic object imaginable, the black hole, a place where relativity's geometry crushed matter to infinite density, and where quantum mechanics, if it dared to enter, seemed to lose its very meaning. It was into that silent chasm that a young man named Stephen Hawking ventured. By 1974, he was 32 years old, already a fellow of Gonville and Caius College, Cambridge, and already paralysed from the neck down by a disease that doctors had expected to end his life more than a decade earlier. But Hawking was not dying. He was thinking, and his mind was ranging across the cosmos, chasing questions so large that most people couldn't even phrase them properly. He had started with cosmology, the origin of the universe itself, but soon found himself fascinated by black holes. To him, they were not dead ends, but puzzles, meeting points of the two great theories of the 20th century. If you could make sense of a black hole, perhaps you could finally unify quantum mechanics and general relativity. He liked to joke that a black hole was where God divided by zero. It was funny, but not entirely untrue. At the time, most physicists treated black holes as theoretical curiosities. They were part of the mathematical furniture of Einstein's equations, but not something that needed the attention of quantum field theorists. After all, relativity dealt with space-time curvature, smooth, continuous, deterministic. Quantum mechanics was grainy, probabilistic, and noisy. The two lived in different worlds. Mixing them seemed as futile as trying to paint a waterfall with solid blocks of marble. But Hawking wasn't satisfied with that separation. He wanted to know what really happened at the edge, at the event horizon, where gravity grows so intense that light itself cannot escape. What would a quantum field look like there? What would the vacuum, that roiling sea of virtual particles, do under such gravitational stress? To explore this, he combined the tools of two incompatible worlds. He took quantum field theory, the mathematical framework that describes how particles behave in spacetime, and applied it to the curved spacetime around a black hole, described by general relativity. It was a risky hybridization, like bolting the engine of a spacecraft to the hull of a submarine, but it worked. In the language of quantum theory, what we call empty space is not truly empty. It's a fluctuating energy field, constantly producing pairs of virtual particles, one positive, one negative, that immediately annihilate each other. Normally, this happens everywhere, all the time, leaving space apparently calm. But near an event horizon, the rules shift. Gravity's pull is so steep that one particle of the pair can be captured before annihilation occurs, while the other escapes. From far away, it looks as if the black hole has emitted a real particle, and because energy has left the system, the black hole must lose a tiny bit of its mass. The mathematics that led to this was unforgiving. Hawking used what's called the Bogolyubov transformation, a formalism that relates how quantum states defined in one region of spacetime transform when viewed from another. To a distant observer, the vacuum outside the black hole appeared to be populated by a thermal spectrum of particles, a kind of glow. A black hole, it seemed, radiated like a blackbody, with a temperature inversely proportional to its mass. In other words, the smaller the black hole, the hotter it glows. It was a breathtaking result, and it made no intuitive sense. According to general relativity, nothing could escape a black hole. Its event horizon was the ultimate one-way membrane. But Hawking's equations said otherwise. Black holes should slowly leak energy, like an ancient kettle, hissing its final steam into the cold of space. When he first saw the result appear in his calculations, Hawking didn't believe it. He assumed he'd made an algebraic mistake. He went over the math again and again, adjusting assumptions, checking constants, recalculating integrals by hand. But each time, the answer returned unchanged. Radiation. A perfect thermal spectrum, just like a star, but faint, almost unimaginably faint. He later recalled, "I found, to my great surprise, that the black hole radiated exactly as if it were a hot body, with a temperature proportional to its surface gravity." The phrase, "to my great surprise," was Hawking's version of astonishment. In the restrained dialect of theoretical physics, that's the equivalent of shouting. When he presented his findings to his peers, the reaction was disbelief bordering on irritation. At the University of Oxford, one senior physicist reportedly muttered, "This can't possibly be right. Black holes don't do that." The result seemed to violate the most sacred principle of the event horizon, that nothing, not even light, can cross outward. And yet, Hawking's mathematics was impeccable. It wasn't that something escaped from inside, it was that the quantum vacuum outside the horizon had been altered in a way that created the illusion of escape. The radiation didn't come from inside the black hole, but from the space just outside it, from the distortion of quantum fields in curved space-time. That subtle distinction was easy to miss, and even easier to mock. To many, it sounded like metaphysical sleight of hand, particles appearing from nowhere, radiation from nothing. Even Hawking himself hesitated to believe the full implications. He had, unintentionally, united three pillars of physics, thermodynamics, relativity, and quantum theory, into a single equation. It was elegant, but also heretical. In 1974, Hawking submitted his paper to Nature, one of the world's most prestigious journals. It was titled Black Hole Explosions, with a question mark, as if he himself wasn't quite ready to remove the doubt. The paper was only 2.5 pages long, but it detonated through the community like a small mathematical bomb. For decades, physicists had assumed that black holes could only grow, that their horizons could only expand as they consumed matter. Now Hawking was suggesting the opposite, that black holes shrink, slowly, inevitably, until they vanish. A few months later, he published a longer and more detailed version in Communications in Mathematical Physics, laying out the derivation in full. There was no longer a question mark in the title. He was sure. It's hard to overstate how radical that claim was. Imagine being told that the laws of thermodynamics, once confined to kettles, engines, and ice cubes, also govern the behaviour of the cosmos's darkest abysses. That even the act of falling into a black hole has a kind of thermal footprint. It was as if someone had found temperature inside geometry itself. The scientific community's reaction was divided. Some physicists were exhilarated, others dismissed it as a mathematical curiosity with no physical reality. After all, if the radiation was as faint as Hawking predicted, there was no conceivable way to detect it. A solar mass black hole, for instance, would emit radiation with a temperature of about 60 nanokelvin, 100 million times colder than the space around it. No telescope, not even in the distant future, could hope to measure that glow directly. And yet the logic was too beautiful to ignore. Jacob Bekenstein, whose entropy idea had inspired the work, wrote to Hawking congratulating him, "I told you they had entropy." Hawking, famously stubborn, replied, "Yes, but it's mine now." It was a half-joking, half-serious rivalry, but beneath it lay genuine admiration. Bekenstein had guessed, Hawking had proved. Still, for all its elegance, the idea left Hawking intellectually isolated. He was respected, even revered, but few truly understood the depth of what he had done. The combination of relativity and quantum mechanics was so technically demanding that only a handful of people in the world could follow every step of the calculation. Those who could often disagreed with the interpretation, and those who couldn't sometimes dismissed it altogether. But Hawking had a rare advantage. He wasn't afraid of contradiction. His illness had taught him a strange kind of patience. He once said that knowing he might not live long gave him a sense of urgency, but also of detachment, that the usual anxieties of reputation, career, or recognition seemed trivial compared to the enormity of the questions he was asking. He worked from home most days, surrounded by books, notes, and the mechanical clatter of his electric wheelchair. Students and colleagues described how he would sit silently for minutes at a time, then suddenly burst out with an idea so unexpected that it changed the direction of the conversation entirely. There's something almost cinematic about those moments. The quiet man, trapped in a fragile body, staring into equations that describe collapsing stars and infinite darkness. And then, the flash of realization that even those monsters must fade. That nothing, not even gravity, can escape the logic of thermodynamics. It's difficult not to see the poetry in it. As his muscles withered, he was describing how the universe itself would one day lose its strength. When the paper finally gained traction, it didn't just alter the physics of black holes, it altered the physics of everything. Because if black holes emit radiation, they must have entropy. And if they have entropy, they must carry information. And if they evaporate, that information must go somewhere. That single chain of reasoning set off 50 years of debate, the black hole information paradox, still unresolved today. But at the moment of discovery, Hawking wasn't thinking about paradoxes. He was thinking about balance, the equations of the universe, which had seemed so divided, gravity on one side, quantum mechanics on the other, were, for a fleeting moment, speaking to each other. Through him, they had found a common voice. It's remarkable how often in science, breakthroughs happen not through new experiments, but through new ways of asking old questions. Hawking's genius lay not just in his mathematics, but in his refusal to accept boundaries, disciplinary or otherwise. He moved freely between cosmology and quantum theory, philosophy and physics, using imagination as his laboratory. He said, "I'm just a child who never grew up. I still keep asking these how and why questions." That childlike curiosity was what allowed him to see that even the most absolute rules might bend, ever so slightly, at the edge of a black hole. For all its elegance, Hawking radiation remains to this day unobserved directly. But indirect evidence, from simulations, analog systems, and theoretical consistency, supports its reality. In laboratories on Earth, physicists have created acoustic black holes using ultra-cold gases, where sound waves play the role of light, and even these systems seem to emit faint analogues of Hawking radiation. The universe, it seems, agrees with his equations. Looking back, the year 1974 stands as one of those pivot points in human thought, like 1905, when Einstein redefined space and time, or 1925, when Heisenberg and Schrödinger birthed quantum mechanics, a quiet moment in a quiet office, and the cosmos changed its story. The universe, once thought to end in eternal darkness, now shimmered with the faintest hint of a final glow. Even black holes, once symbols of annihilation, became participants in the cosmic cycle, absorbing, radiating, and finally disappearing. And though Hawking could never have known it then, his discovery would ripple outward far beyond physics. It would inspire philosophers to rethink the nature of information, theologians to reconsider creation, and artists to imagine the universe not as a static machine, but as a living process of transformation and decay. A whisper of radiation from the edge of forever, echoing all the way back to us. Hawking himself rarely indulged in sentiment. He preferred irony. When journalists asked how he felt about discovering that black holes evaporate, he replied dryly, "It means that I am on the losing side of the argument with thermodynamics." And then, with a faint smile, added, "But it's good to know the universe has a sense of humour." By the end of 1974, he was a celebrity in the world of physics, invited to conferences, celebrated in journals, and quietly preparing to reshape cosmology once again. His voice, still clear then, would soon weaken, replaced by the synthetic monotone that would become world-famous. But before that happened, he had already given the universe a new voice of its own, the faint, mathematical whisper of Hawking radiation. And in that whisper was a message more profound than even he perhaps realized, that darkness is never complete, that even in the silence of gravity, the laws of quantum mechanics find a way to speak, and that in the end, everything, even the black hole, must learn to let go. Space looks empty. We look up at the night sky, between the stars, and we call it a void. We imagine the vacuum of space as a cold, perfect nothing, a kind of infinite silence where light travels freely and time glides without friction. But physics, with its annoying habit of ruining simplicity, says otherwise. The vacuum is not empty, it's restless, alive and seething with invisible activity. What we call nothingness is, in truth, a boiling sea. Quantum field theory, our best description of the subatomic world, says that everything in existence, from electrons to photons to neutrinos, is just an excitation of an underlying field. These fields fill all of space. Even where there are no particles, the fields remain, fluctuating around what we call their ground state. And because of the uncertainty principle, that quiet law that forbids perfect stillness, they can never stay completely calm. At every point in space, tiny fluctuations are occurring all the time. They rise and fall, creating ephemeral particle-antiparticle pairs that appear out of nowhere, exist for a fleeting instant, and then annihilate each other back into energy. This is the quantum vacuum. In human terms, it's like the surface of the sea seen from far above. From a distance, it looks smooth and tranquil. But up close, the surface is alive with motion, waves forming and collapsing, bubbles rising and bursting. Even when the sea looks calm, it's never truly still. That's the quantum vacuum. Calm only when you don't look too closely. These virtual particles, the bubbles on the surface of reality, are constantly being born and destroyed. They're called virtual not because they're imaginary, but because they don't last long enough to be observed directly. They are a borrowing, a brief loan of energy from the universe, allowed by the uncertainty principle, as long as it's repaid quickly. It's the cosmic equivalent of overdrawing your account and paying it back before anyone notices. Sometimes these momentary fluctuations leave real traces. In the famous Casimir effect, if you place two metal plates very close together, just a few nanometers apart, they experience a tiny attractive force. No classical explanation exists for it. There's no air between them, no magnetism, no static. What's happening is that the plates restrict the kinds of virtual particles that can form between them, slightly lowering the energy there compared to the space outside. The plates are literally pushed together by the pressure of the quantum vacuum. Nothingness, it turns out, can shove. The same restless vacuum causes a phenomenon called Lamb shift, a subtle change in the energy levels of hydrogen atoms measured with exquisite precision in the 1940s. The prediction and later confirmation of that shift was one of the great triumphs of quantum electrodynamics. It proved that even the smallest ripples in empty space could influence the behavior of matter. The void was no longer a void. It was an ocean with waves too small for us to see. This ocean exists everywhere, including the regions around black holes. And it was here that Hawking's insight took shape. Imagine the region just outside a black hole's event horizon. The invisible boundary where gravity's pull becomes so extreme that even light cannot escape. The quantum vacuum there isn't calm. Pairs of virtual particles are constantly popping into existence, just as they do everywhere else in the universe. Normally, these pairs appear together, live together, and disappear together, one with positive energy, one with negative, annihilating in a flash so brief that it defies measurement. But near a black hole, something different can happen. Picture it as a pair of dancers appearing at the edge of a cliff. They spin together for a heartbeat, and then one of them slips and falls. The other manages to leap away. In the vacuum, that cliff is the event horizon. Gravity pulls one particle inward before it can reunite with its partner. The other escapes to infinity. And because they can no longer annihilate, the escaped particle becomes real. It carries energy away, visible as radiation. From the perspective of an observer far away, it looks as if the black hole itself has emitted that particle. But the black hole has paid a price. Energy has left the system. And according to Einstein's most famous equation, energy and mass are interchangeable. So the black hole's mass decreases ever so slightly. That's the essence of Hawking radiation. It's a strange process because it involves three layers of reality interwoven in a single act: quantum mechanics, which allows the fluctuation relativity, which defines the curvature of space and the horizon, and thermodynamics, which dictates the balance of energy and entropy. All three whispering the same story, that even the darkest places in the universe are still connected to everything else. If you could somehow watch this happen, it would look almost serene. No flashes, no bursts, just a slow, steady glow of particles being born from the edge of gravity's dominion. each one carrying away a fraction of mass, a hint of information, a sliver of the black hole's identity. Over unimaginable timescales, this trickle of energy will drain the black hole completely until it vanishes, a cosmic evaporation. But that takes longer than the lifetime of stars, galaxies, or perhaps the universe itself. In that sense, Hawking radiation is not just physics, it's a meditation on time. It reminds us that permanence is an illusion. Even the things that appear eternal, black holes, space, the universe, are in motion, decaying, transforming. The vacuum's fluctuations ensure that nothing ever truly stays still. If the quantum vacuum sounds mystical, it's because it blurs the line between existence and non-existence. In classical physics, something either is or isn't. But quantum theory tells us that nothing is unstable, that it wants to become something, even if only for a fleeting instant. It's like a stage where actors constantly step out from behind the curtain, deliver a line, and vanish again before the play can begin. The script is written in probabilities. The performance is perpetual. The universe itself may have begun this way, as a quantum fluctuation that refused to cancel out. In that sense, the birth of everything may have been an especially ambitious vacuum event, a brief imbalance that grew into space, time, and everything we now see. So when Hawking described black holes evaporating through the theft of virtual particles, he was touching on the same deep principle that may have birthed the cosmos, creation from nothing, but nothing that was never truly nothing to begin with. It's worth pausing on that contradiction, because it says something profound about the nature of reality. We think of something from nothing as a paradox, a violation of logic, but in physics, nothing has structure. It has rules. The vacuum is a medium, invisible, yes, but full of potential energy. And like a stretched fabric, it can ripple. A ripple in that fabric is what we call a particle. A deeper ripple, one that traps light and time itself, is what we call a black hole. In this view, everything that exists is just the vacuum behaving differently. There's a quiet elegance to that idea. Matter, energy, radiation, gravity, all are expressions of the same underlying field, like different notes in the same cosmic chord. Even destruction is just transformation. The black hole doesn't truly destroy energy or information. It redistributes them, diffuses them, blends them into the fabric from which they came. The whisper of Hawking radiation is that reminder. The universe never stops talking to itself. Still, there's a question that haunts physicists. If the escaping particle has positive energy, then the one that fell into the black hole must have negative energy relative to the outside world. That's what causes the black hole to lose mass. But what does negative energy really mean? It's not the kind of energy you can measure with a battery or a thermometer. It's an accounting concept, a way of saying that the gravitational field has given up a tiny piece of itself. The black hole shrinks, the universe gains a little radiation, and the ledger stays balanced. Even at the edge of chaos, the books of physics are meticulously kept. When we try to describe this process without mathematics, we have to rely on metaphors, and metaphors, while useful, can mislead. It's tempting to imagine particles leaping out of black holes or escaping from within, but the truth is subtler. The radiation doesn't come from inside the horizon, but from the interplay of quantum fields outside it. The horizon is more like a border of perception, a place where what's real and what's virtual trade places. One partner falls into a region where time and space are so distorted that it can never return. The other becomes free, visible, real. In a sense, the black hole pays for that freedom with a piece of itself. It's easy to miss how audacious that idea is. Before Hawking, black holes were the ultimate symbol of finality, regions of no return where all processes stop. After Hawking, they became active participants in the universe's thermodynamic economy. They radiate, cool, and eventually vanish. They are not graves, but slow transformations. To picture it more intuitively, imagine space as a vast, invisible fabric stretched across the universe. Wherever there's mass, the fabric dips. A black hole is a place where the dip becomes so steep that nothing can climb out. But the quantum vacuum doesn't care about such macroscopic drama. Its fluctuations ripple across every contour of that fabric. At the steep edge, some ripples get trapped, others escape. Over eons, those escaping ripples carry away energy, gently smoothing out the dip until one day the fabric is flat again, the black hole erased not by violence, but by patience. It's a process so delicate that it borders on poetry. The most violent objects in the universe, born from the collapse of stars with gravitational fields strong enough to crush atoms and warp time, are undone not by explosions, but by whispers, by the faintest possible glow, by the quiet hum of virtual particles that no one will ever see. The universe ends not with a bang, perhaps, but with a sigh of Hawking radiation. When you think about it that way, the vacuum becomes a kind of artist, sculpting existence from silence, eroding even the most unyielding forms with its constant, invisible touch. In the human world, we call this impermanence. In physics, we call it entropy. But at the deepest level, it may just be the vacuum doing what it has always done, exploring every possibility, one fluctuation at a time. There's a certain humility that comes from realizing that everything we see, stars, galaxies, black holes, you and me, is made of excitations in this quantum sea. Matter is just the vacuum vibrating in slow motion. Energy is its rhythm. Space itself is its stage. And gravity, perhaps, is the choreography that keeps the dance coherent. When Hawking found that a black hole could radiate through this process, he wasn't merely describing a physical mechanism. He was pointing to a deeper truth, that nothingness is not an absence, but a presence too vast to perceive, that the universe's silence hums beneath everything we call real, that even emptiness, left alone long enough, will create, destroy, and sing. We tend to think of discovery as the act of finding something new, but sometimes it's about finding something subtle, something that was there all along, waiting for the right question. The quantum vacuum had been part of physics for decades before Hawking, but few had asked what it might do near the edge of a black hole. He asked, and the void answered. The answer was quiet, but it changed everything. Thermodynamics was never meant to describe the cosmos. It was born in the age of steam, in the 1800s, when physicists were trying to understand why engines could never be perfectly efficient. They discovered a set of laws, simple, universal, and quietly profound. No matter how clever your design, you could never extract all the energy from heat. Some would always slip away into disorder, into entropy. That loss wasn't mechanical. It was fundamental. It was the universe insisting that perfection has a cost. From those practical origins grew something extraordinary, a framework that describes not just machines, but all of reality. Thermodynamics is the physics of limits, how energy moves, transforms, and ultimately spreads out. It is the story of how order becomes chaos, and strangely, that story turns out to apply even to black holes, objects that seem at first glance to be the very embodiment of order and simplicity. In 1972, a young graduate student at Princeton named Jacob Bekenstein made a heretical suggestion. He was studying under John Archibald Wheeler, the physicist who had coined the term black hole. At the time, Wheeler and his colleagues were exploring the theoretical behavior of these objects, how they absorb matter and interact with the rest of the universe. The equations of general relativity described black holes as perfect one-way traps. Nothing could escape their pull. Anything that fell in disappeared forever, and the black hole itself could be described by only three parameters: mass, charge, and spin. This became known as the no-hair theorem. Everything else, every detail about what fell in, was lost. Bekenstein found this deeply unsettling, because if black holes really erase information, then one of the most sacred principles of physics, the conservation of information, might be broken. And if they don't erase it, then something else must be happening to that information inside. He began to suspect that the surface of the event horizon, the invisible boundary, might hold the key. He noticed an intriguing parallel between black holes and thermodynamic systems. When you throw matter into a black hole, its mass increases, and its event horizon grows larger. In thermodynamics, when you add heat to a system, its entropy increases. The two processes looked eerily similar. Perhaps, Bekenstein thought, the surface area of a black hole is a measure of its entropy, the amount of information it conceals. At first, That idea seemed absurd. Entropy is a measure of disorder, the number of microscopic configurations that correspond to a system's macroscopic state. It's the difference between knowing how many ice cubes are in your glass and knowing the position of every single water molecule within them. But a black hole, by definition, erases those details. How could something that hides information also measure it? Yet, the analogy wouldn't go away. When you drop something into a black hole, the event horizon grows. The increase in area behaves exactly like an increase in entropy. It never decreases. No process, according to general relativity, can make the surface area of a black hole shrink. It was as if nature had smuggled the second law of thermodynamics into the geometry of spacetime itself. Bekenstein proposed a bold equation. The entropy of a black hole, S, is proportional to the area of its event horizon, A, not its volume, as one might expect, but its surface area. That distinction was radical. It implied that the information contained within a region of space is encoded not in its interior, but on its boundary. Reality, in a sense, might be holographic, but in 1972, Bekenstein wasn't thinking of holograms. He was thinking of survival. He wanted the laws of physics to remain consistent even in the presence of black holes. The idea was met with skepticism. Most physicists thought he was simply trying to stretch an analogy too far. Hawking, then already a rising figure in gravitational physics, was among his critics. He dismissed the notion, saying it didn't make sense to assign entropy to something that could only absorb energy, never release it. A black hole, he argued, had no temperature, no internal motion, no way to radiate. It was the coldest thing imaginable. Thermodynamics didn't belong there, but 2 years later, Hawking's own calculations forced him to reconsider. When he discovered that black holes emit radiation, the picture changed completely. If they can radiate, they must have temperature, and if they have temperature, then by definition, they must have entropy. Bekenstein's intuition was right. The equation that emerged from Hawking's work became one of the most beautiful in all of physics. The entropy of a black hole is equal to 1/4 of its event horizon area, measured in Planck units. That 1/4 factor, 1/4, might seem trivial, but it encodes the bridge between gravity, quantum mechanics, and thermodynamics. It links 3 universal constants: the speed of light, the gravitational constant, and Planck's constant. In that single relation, the vast scales of the cosmos and the tiny realm of the quantum meet in harmony. For a physicist, it was like hearing the universe hum in tune for the first time. It also created one of the strangest inversions in science, the idea that surface area, not volume, measures information. In everyday life, the more space something occupies, the more stuff it can contain. But for black holes, that's not true. All the information about everything that has ever fallen in is stored on the 2-dimensional surface of the horizon. It's as if the universe writes its secrets not in its depths, but on its skin. That insight would later inspire the holographic principle, a cornerstone of modern theoretical physics. The idea that all the information contained in a region of space can be represented on its boundary. But in the 1970s, it was still just a curious pattern, a whisper of something deeper. What made this realization so powerful was how it unified disciplines that had always seemed separate. Thermodynamics describes energy and entropy. General relativity describes space-time and gravity. Quantum mechanics describes probability and uncertainty. Hawking radiation and Bekenstein's entropy connected them all. They revealed that gravity has a temperature, that space-time can radiate, that geometry itself can obey the laws of heat and information. It meant that black holes aren't just astrophysical oddities, they're laboratories for fundamental physics. By studying them, we can glimpse how the universe's deepest laws intertwine. The 4 laws of black hole mechanics, as they came to be called, mirror the classical laws of thermodynamics almost perfectly. The first law relates changes in a black hole's mass, area, and spin to its energy, much like the first law of thermodynamics relates heat and work. The second law, that the total horizon area of black holes can never decrease, echoes the second law of thermodynamics, which states that entropy never decreases. The third law, about reaching absolute zero, has its gravitational counterpart. It's impossible to reduce a black hole's surface gravity to zero through any physical process. Even the zeroth law, the constancy of temperature in thermal equilibrium, finds its twin in the constancy of surface gravity across a stationary horizon. It's as if nature rewrote the laws of heat into the language of space-time. This unity brought something philosophical too, a sense that the universe has a kind of thermodynamic morality. Order inevitably decays, energy spreads, and even the most powerful gravitational structures obey that law. Entropy, in this view, is not chaos. It's honesty. It's the universe acknowledging that perfection can't last. To think that a star once blazing with nuclear fire could collapse into a black hole, and that this black hole, in turn, has a temperature and entropy, is to realize that the chain of transformation never ends. There is no final state, only deeper layers of balance. And yet this balance carries a haunting implication. If black holes have entropy, then they have information. And when they evaporate, that information must go somewhere. Does it leak out with the radiation? Does it remain encoded in some subtle way? Or does it vanish, violating the fundamental principle that information can't be destroyed? These questions formed the heart of the black hole information paradox, the mystery that would consume decades of debate and inspire new theories of quantum gravity. But even before that paradox emerged, the conceptual shift was enormous. Black holes had gone from being endpoints to being participants, from cosmic voids to thermodynamic systems. And in that transformation, physicists glimpsed something spiritual. Entropy, after all, is not just about disorder, it's about possibility. A system with high entropy is one that can take many forms. It's flexible, adaptive, and alive in its own statistical way. The black hole, seen through this lens, isn't dead. It's the most complex object in the universe, containing the maximum amount of information possible for its size. It is paradoxically both the simplest and the richest thing that can exist. That realization changed how physicists think about information itself. It's no longer something abstract, confined to libraries or databanks. Information is physical. It's woven into the fabric of reality. Every bit of matter, every photon of light, carries it. When information disappears from one place, it must appear somewhere else. Hawking radiation may be the mechanism by which the universe keeps its books balanced, a cosmic redistribution of knowledge. This idea leads to one of the most poetic equations ever written, the Bekenstein-Hawking entropy formula. It combines the constants of nature, gravity, quantum mechanics, and thermodynamics, into a single statement. And when you calculate it, you find that a black hole with the mass of the Sun has an entropy of roughly 10 to the 77th power joules per Kelvin, unimaginably large. For comparison, the entropy of the Sun itself, as a star, is only about 10 to the power of 58. A black hole is not a simple thing. It is a vault of cosmic complexity, compressed into a silence so complete that only mathematics can describe it. Perhaps that's why physicists speak of black holes with such reverence. They're not just objects, they're teachers. They tell us that every act of collapse conceals not emptiness, but structure. That every loss hides a deeper conservation. That entropy is not the end of meaning, but the measure of it. In the end, Hawking and Bekenstein had uncovered something larger than either expected. By uniting the physics of the infinitely large with that of the infinitesimally small, they had found a glimpse of the universe's architecture, a place where geometry and heat, gravity and information all meet in the same equation. The abyss, it turns out, obeys the same rules as a cup of tea cooling on a table. It's just that the table is space-time, and the tea is a dying star. When you think about that, it becomes hard not to feel a quiet awe. Every black hole, silent and invisible, is a monument to the laws of balance, a testament that even in the cold depths of gravity, the warmth of thermodynamics persists, and in its faint radiation, that almost undetectable whisper, we can hear the universe reminding itself that nothing is lost, only changed. When we talk about temperature, we usually mean something familiar, the warmth of sunlight on your skin, the chill of metal in winter, the comforting steam of tea rising in a quiet room. Temperature feels human. It's the measure of how fast things move, how particles vibrate, how energy spreads through matter. In everyday life, it's a scale of comfort and survival. But out in the cosmos, temperature has meanings that stretch far beyond sensation. It can describe the faint background glow of the universe itself, the fusion in a star's heart, or the almost imperceptible warmth of a dying black hole. And it is here, at the intersection of extremes, that one of nature's strangest inversions appears. The smaller a black hole becomes, the hotter it gets. At first glance, that makes no sense. We're used to thinking of big things as hot, stars, furnaces, engines, and small things as cool. But black holes play by different rules. Their temperature, called the Hawking temperature, depends inversely on their mass. In simple terms, large black holes are cold, and small ones burn like cosmic embers. The formula itself, derived from the combination of quantum mechanics, general relativity, and thermodynamics, is deceptively compact. It shows that the temperature is proportional to the surface gravity of the black hole and inversely proportional to its mass. So as a black hole loses mass through Hawking radiation, its temperature rises. As it gets hotter, it radiates faster, which makes it lose mass even more quickly. A runaway process, a slow burn that accelerates toward oblivion. It's a kind of cosmic irony. Everything else cools as it loses energy. Black holes get hotter. They defy the intuitive sense of decay. They die not by fading into cold, but by heating themselves into extinction. For a black hole the mass of our Sun, this temperature is unimaginably low, about 60 nanokelvin. That's 60 billionths of a degree above absolute zero. The coldest known natural places in the universe, such as the Boomerang Nebula, hover around 1 Kelvin or minus 272 degrees Celsius. Even that frigid cloud is 10 million times warmer than a typical stellar black hole. By any human or even cosmic standard, such a black hole is not just cold, it's effectively frozen. The universe around it, however, is not. Everywhere in space, there is a faint afterglow, the cosmic microwave background, the remnant heat of the Big Bang. It fills the cosmos at about 2.7 Kelvin, or roughly minus 270 degrees Celsius. That gentle radiation bathes everything, stars, planets, black holes, in an invisible warmth. And because 2.7 Kelvin is vastly higher than 60 nanokelvin, a typical black hole doesn't radiate energy outward. It absorbs more energy from the universe than it emits. In other words, the cosmos is still too hot for black holes to begin truly evaporating. Only when the universe cools below their own temperature, long after the last stars have burned out, will black holes begin to lose mass faster than they gain it. It will take trillions upon trillions of years before that balance tips. But eventually, it will. In that distant era, sometimes called the black hole epoch, the universe will be a very different place. Galaxies will have thinned into sparse collections of dark remnants, dead stars, frozen planets, and the enormous black holes left behind. There will be no starlight, no warmth, no new chemistry. The cosmic microwave background will have stretched and cooled through the relentless expansion of space until its temperature falls below that of the smallest black holes, and then, slowly, almost imperceptibly, they will begin to glow. The first to evaporate will be the smallest, the so-called primordial black holes, if they exist at all. These would have formed shortly after the Big Bang, from tiny fluctuations in the density of the early universe. Most would be microscopic by now, smaller than atoms, evaporating violently in a final flash of gamma rays. Their deaths, if they occurred, would be brief fireworks in the immense night. Larger black holes, like those born from collapsing stars, will take much longer, about 10 to the power of 66 years, for one the mass of our Sun, and perhaps 10 to the power of 100 years or more for a supermassive black hole. To put that in perspective, the current age of the universe is 13.8 billion years, 1.38 times 10 to the power of 10 years. So a stellar black hole's evaporation will take about 10,000 billion times longer than all of history so far. It's a number so vast that it's almost indistinguishable from eternity. But physics is patient. Given enough time, even eternity yields results. As the black hole loses mass, its surface area shrinks and its temperature rises. By the time it has the mass of Mount Everest, it would radiate at about 10 trillion Kelvin, hotter than any known star. Near the end, it would release enormous amounts of energy in a final burst of radiation, a brief blaze before silence. The smaller it gets, the faster the process accelerates until, in the final fraction of a second, the black hole's temperature and luminosity spike to infinity and it vanishes. No one knows exactly what that last moment looks like. Our physics breaks down at such extremes. Some models predict a bright gamma-ray flash, others a fading whisper of energy dispersing into the void. Some theorists suggest that the evaporation stops at a certain point, leaving behind a relic, a stable remnant containing the information of everything that ever fell in. But if Hawking's equations hold true to the end, then even that remnant eventually dissolves. Nothing remains. It's hard to imagine such timescales. When we speak of billions of years, we're already stretching human comprehension. But here, we're talking about powers of 10 stacked 100 deep, times so long that even protons may have decayed long before the black holes finish their slow fade. During those epochs, the universe will be silent and nearly empty. All structure, stars, planets, even atoms, will have unraveled. Only black holes, those ancient engines of gravity, will persist. They will outlast galaxies, light, and memory, and then, one by one, they too will vanish. When the last one goes, the universe will be filled with low-energy photons and neutrinos drifting through space so vast that they may never meet another particle again. That will be the end of the thermodynamic story, when entropy reaches its maximum and no more work can be done. The universe will have achieved what physicists call heat death, a state of perfect equilibrium, perfectly still, perfectly unremarkable. Everything that can happen will have happened. It's strange to think of heat death as an ending, because the phrase suggests fire, destruction, some final blaze of collapse. But it's the opposite. It's not an inferno, but a calm, a levelling out, the slow evening of all differences. Temperature itself, that measure of contrast, will cease to have meaning. Everything will be the same everywhere. And yet, it's that sameness that gives the present its vitality. Because we live in a universe that is still unbalanced, where temperatures differ, where energy flows, where gravity gathers matter into stars and planets, and minds capable of wondering about all this. Life, motion, thought, all are temporary structures carved from imbalance. Entropy ensures that they can't last, but it also ensures that they can exist in the first place. When Hawking derived the temperature of a black hole, he didn't just add a number to physics, he added a metaphor. He showed that even the most extreme objects are part of the same thermodynamic continuum as everything else, as our own breath, as the glow of a candle, as the fading warmth of a dying star. The laws that govern boiling water in a pot are the same ones that describe the evaporation of a black hole over 166 years. Different scales, same rhythm. There's an almost spiritual symmetry in that. It means that the universe, in all its enormity, still plays by rules we can understand. That we, in our small kitchens and observatories, are participants in the same great system of heat and change. That every flicker of warmth, every cooling ember, every faint glow in the cosmic night is part of a universal dialogue between energy and entropy. The Hawking temperature may be impossibly low, but its meaning is immense. It ties together gravity and quantum mechanics, two realms that had resisted union for a century. It hints that spacetime itself is not just geometry, but a thermodynamic entity capable of storing and radiating heat. And it suggests that information, the deepest currency of reality, is never truly destroyed, only diffused into the fabric of existence. From a certain point of view, Hawking radiation is the universe remembering itself. Each particle that escapes carries away not just energy, but a trace of the black hole's history, written in the language of probability. If we could decode that faint thermal glow, perhaps we could reconstruct the story of everything that ever fell in. The light of long-dead stars, the dust of ancient worlds, the equations of thought from minds now gone. In practice, we never will. The signal is too faint, the time too vast, but the principle remains. Nothing truly vanishes without leaving an echo. It's poetic, then, that the coldest things in existence are also, in their final moments, the hottest. That black holes, those icons of silence, end in fire. That creation and destruction, heat and cold, light and dark, are simply phases of the same ongoing conversation. And when the last one evaporates, when the last photon escapes into an ocean of almost nothing, the universe will fall quiet, not in tragedy, but in completion. Every process will have run its course, every imbalance will have resolved, every flame will have burned to equilibrium. The temperature of darkness will be universal, a perfect, eternal 0 point, unchanging and complete. That is the ultimate paradox Hawking revealed, that even the blackest silence has a temperature, that even the void has a pulse, and that the end of all things is not a catastrophe, but a symmetry. And perhaps, if the universe could feel, it would find comfort in that, in knowing that its final act is not chaos, but peace. Time is not the same everywhere. We experience it as a steady rhythm, seconds, minutes, years. But in the universe, time stretches and contracts, depending on gravity and motion. To a black hole, the difference between 1,000,000 years and 1,000,000,000,000 might be as small as a heartbeat. And to us, looking out from this tiny world, the lifetime of a black hole is almost indistinguishable from eternity. Yet eternity in physics is not infinite. Even the longest story has an ending. And so black holes, those symbols of permanence, also have a lifespan. When Hawking radiation enters the picture, every black hole becomes a kind of hourglass, its mass slowly trickling away into space. But the pace of that evaporation depends dramatically on its size. The larger the black hole, the slower it fades. The smaller it gets, the faster it burns. In this inverted world of gravity and heat, size determines time. A stellar black hole, formed when a massive star collapses, typically contains between 3 and 30 times the mass of the Sun. At that scale, its Hawking temperature is unimaginably cold, only a few dozen nanokelvin. The radiation it emits is so weak that it's utterly lost in the glow of the cosmic microwave background. To such an object, the universe is still too warm to die. For now, it absorbs more energy than it releases. Its evaporation hasn't even begun. If you could somehow accelerate time and watch the process unfold, you'd find that a black hole with the mass of the Sun would take around 10 to the power of 66 years to vanish. That's a 1 followed by 66 zeros. Compare that with the universe's current age, 13.8 billion years, and it's almost impossible to hold both numbers in the same thought. It's like comparing a single breath to the lifetime of galaxies. Supermassive black holes, the titans at the centres of galaxies, stretch the timeline even further. The one anchoring the Milky Way, Sagittarius A star, is about 4 million solar masses. The monster at the centre of the galaxy M87, famously imaged by the Event Horizon Telescope in 2019, is about 6.5 billion solar masses. For black holes of that scale, evaporation takes at least 10 to the power of 99 to 10 to the power of 100 years. They will be the last beacons of gravity in the farthest conceivable future, long after the stars have gone out, when galaxies have drifted beyond each other's reach, when protons have decayed into light. The supermassive black holes will remain quiet, dark, patient. But even patience has a limit. Over eons, they too will begin to lose their grip. Their slow leakage of Hawking radiation will become noticeable only when the cosmic microwave background has cooled below their own temperature. By then, the universe will have aged beyond comprehension. Distances between galaxies will have expanded so vastly that light from one may never reach another again. Entropy will have nearly completed its work. A curious inversion will occur at that point. The biggest black holes will become the last sources of warmth in an otherwise frozen universe. Each one, radiating faintly, will stand as a solitary lantern in an endless night. And then, one by one, they will flicker out. The final stages of evaporation are where theory becomes both thrilling and uncertain. As a black hole loses mass, its temperature rises. At first, this acceleration is slow, Centuries or millennia pass with barely any change, but as the mass decreases, the radiation strengthens and the end approaches faster. When the black hole's mass drops to that of a mountain, roughly 1 billion tons, its temperature will soar to trillions of Kelvin, releasing energy comparable to that of 1 billion hydrogen bombs in a fraction of a second. At that stage, it will emit a final burst of gamma rays, the highest energy photons known, along with a storm of particles, electrons, positrons, neutrinos, perhaps even quarks and gluons. It will vanish in light. No one has ever seen such an event. But if primordial black holes, those formed in the chaotic first moments after the Big Bang, exist, some of them might be reaching that stage right now. In the early universe, the density of matter was not uniform. Tiny fluctuations, random ripples in the fabric of space-time, could have collapsed under their own gravity to form miniature black holes, some no heavier than mountains, others no heavier than asteroids. These would have been small enough for Hawking radiation to affect them within the current age of the universe. A primordial black hole of about 10 to the power of 12 kilograms, roughly the mass of a large mountain, would evaporate in about 13.8 billion years. The same age as the cosmos itself. If they were born then, their final explosions could be occurring today. Astronomers have searched the sky for flashes of high-energy gamma rays that might betray these deaths. So far, none have been conclusively identified, but the absence of evidence is not yet evidence of absence. It may simply mean that primordial black holes were rarer than we thought, or that their final bursts are fainter or more complex than expected. If one were to explode within our galaxy, it would shine for a brief moment brighter than 1,000 suns, an invisible fire radiating in wavelengths our eyes can't see. And then, gone. The concept of a black hole explosion seems contradictory. How can something defined by its gravity end in lightness? Yet, this is precisely the paradox that Hawking radiation embodies. The very mechanism that made black holes black also ensures that they are temporary. It's a perfect symmetry. Gravity, which gathers matter, also contains within it the seeds of its own undoing. What begins with collapse ends with dispersal. Creation and evaporation are not opposites. They are complementary gestures in the universe's grand thermodynamic cycle. If we could compress this entire future into a film, billions of years per frame, it would begin with brightness, the age of stars. Then, slowly, the galaxies would dim, stars would die, leaving behind white dwarfs, neutron stars, and black holes. Then, even those remnants would fade. And finally, black holes would begin to evaporate, their Hawking glow brightening as they shrink until the last supermassive one releases its final flare. Then, darkness again, perfect and complete. A cosmic exhalation, ending in silence. The numbers that describe these processes are staggering, yet precise. A black hole with the mass of the Earth would vanish in about 10 to the 50 years. One with the mass of a mountain would disappear in a fraction of a second. A black hole as massive as the Sun would last 10 to the power of 66 years. And a giant of 6 billion solar masses, like the one in M87, would outlive the universe itself, 100 billion years or more before its final moment. Each case follows the same rule. Lifetime increases with the cube of the mass. Double the mass, and the lifespan increases 8-fold. Size buys time, but no size buys immortality. When physicists talk about these timelines, it's tempting to treat them as abstractions, just numbers, neat outcomes of equations. But they carry a deeper meaning too. They remind us that nothing lasts forever, not even the fabric of space. Everything that exists, from the brief life of a particle to the long breath of a black hole, follows the same logic of change. There is no permanence, only process. The eventual death of black holes also tells us something about information, that mysterious property that bridges physics and philosophy. If a black hole evaporates completely, where does the information about what fell in go? Is it lost forever, or encoded somehow in the radiation that escapes? This question, the black hole information paradox, remains one of the greatest puzzles in modern science. But regardless of how it's resolved, the story it tells is profound. The universe keeps its books, even if we don't yet understand how. There's a strange comfort in this vision of cosmic mortality. It shows that impermanence isn't a flaw, it's a feature. The same laws that govern the fading of black holes also govern the fading of stars, the cooling of worlds, the passing of moments. We are built from the same rules. Entropy is not the enemy of meaning, it is the frame that gives meaning shape. In the end, black holes teach us about patience. They evolve on scales so vast that the word eventual loses all practicality. Their deaths are measured not in seconds or years, but in powers of 10 that swallow imagination. And yet, each of those distant numbers is written into the equations of nature, waiting to unfold. Physics has no hurry. The universe has time. When the last black hole dies, trillions upon trillions of years from now, the universe will enter its quietest age. No light, no sound, no structure. Just the smooth glow of low-energy photons diffused through infinite space. It will not be destruction, but completion, the final equilibrium of all that ever was. If the universe could feel, perhaps it would find peace in that. After all, every fire wants to cool, every imbalance wants to rest. And perhaps the greatest act of creation was not the Big Bang, but the long, graceful fading that follows, the universe teaching itself how to let go. When Stephen Hawking announced that black holes could evaporate, the physics community was astonished, not just because of the discovery itself, but because of what it implied. If a black hole slowly radiates away its mass until it disappears, what happens to everything that fell inside? Does all that information, the patterns of matter, the arrangement of particles, the quantum states that once described stars, planets, even people, simply vanish? That simple question opened one of the deepest cracks in modern physics. It became known as the black hole information paradox, and it was not merely a puzzle about black holes. It was a challenge to the very foundation of how reality works. In physics, information has a specific meaning. It's not gossip or data in a computer. It's the set of all measurable properties of a system, the exact configuration of particles, fields, and forces that define it. Quantum mechanics insists that this information cannot be lost. Every process in the universe, no matter how chaotic, is in principle reversible. If you knew the quantum state of every particle at one moment, you could, at least theoretically, run the equations backward and reconstruct the past. It's a rule called unitarity, and it is one of the cornerstones of quantum theory. General relativity, however, has no such law. In Einstein's universe, information is carried by matter and energy, but when something crosses the event horizon, its details are erased from the outside world. To an observer at a distance, only 3 quantities remain visible: mass, spin, and charge. Everything else, chemical composition, shape, structure, is gone. Einstein's equations don't care about the details, they reduce the universe to geometry. Hawking's discovery united these two theories, but it also made them collide. If black holes radiate and eventually evaporate completely, the information about everything they once contained appears to be destroyed. The radiation that escapes is purely thermal, random, like heat from a fire. It carries no memory of what produced it. When the black hole finally vanishes, nothing remains. The universe, once perfectly logical and reversible, suddenly forgets. That forgetfulness is what terrified physicists. Because if information can be destroyed, then the very structure of quantum mechanics collapses. The probabilities that govern atomic behavior, the conservation laws that preserve energy and momentum, even the concept of cause and effect, all would unravel. The loss of information is not a small technical issue. It's a violation of the logic that holds physics together. Hawking himself accepted that grim conclusion. In 1976, he published a paper declaring that black holes cause a fundamental loss of predictability in quantum gravity. He argued that once information crosses the event horizon, it's gone forever. His reasoning was simple but devastating. If the radiation coming out is purely thermal, it contains no structure, no signature of the matter that fell in. The original information cannot be reconstructed. The universe, he said, is not perfectly deterministic. It sometimes destroys the record of its own past. This statement sent shockwaves through theoretical physics. For decades, scientists had struggled to reconcile relativity and quantum theory. Now one of the world's most brilliant minds was saying that reconciliation might be impossible. At conferences, debates grew heated. Nobel laureate John Preskill compared Hawking's claim to burning an encyclopedia and expecting to get the letters back out of the smoke. Leonard Susskind, a theoretical physicist at Stanford, said bluntly, "If Hawking is right, then we must give up on quantum mechanics." And no one wanted to do that. What followed was not just a scientific argument, it was a philosophical war. On one side stood Hawking and those who believed that information can truly vanish behind a horizon. On the other were the defenders of quantum purity, who insisted that nature never erases data, no matter how hidden it becomes. The battleground was the event horizon, that invisible surface separating the knowable from the unknowable. And for 30 years it became the most contested boundary in science. To grasp why the paradox matters, imagine something simple, say throwing a book into a fire. From a classical perspective, the book's information, its words, its ink, its pages, is gone. But from a quantum perspective, it isn't. Every photon of light, every molecule of smoke carries, in principle, the imprint of what was burned. In theory, if you could measure every particle emitted by the fire, you could reconstruct the book exactly. You'd never manage it in practice, of course, but physics says the information still exists. It's scrambled, not destroyed, but if you throw the same book into a black hole, Hawking's 1970s calculations seem to say otherwise. The radiation that comes back out has no imprint, no encoding, no trace of the book's structure. It's as if the universe really did incinerate the text itself, not just its pages. This was intolerable to many physicists. The laws of quantum mechanics had survived every test for a century. They couldn't simply fail at the edge of a black hole. So new ideas began to emerge, attempts to preserve information without contradicting Hawking's equations. One of the most influential came from Leonard Susskind and Gerard 't Hooft in the 1980s and 1990s. They proposed that information isn't lost inside the black hole at all. It's encoded on its surface, like a kind of cosmic hard drive. From the perspective of an outside observer, everything that falls in is smeared across the event horizon, its details stored in the quantum states of that surface. To someone falling in, however, the experience is different. They see themselves passing smoothly through the horizon without noticing anything unusual. This dual perspective became known as black hole complementarity. Both views are valid, but no single observer can witness both at once. Information, in this picture, isn't destroyed. It's simply inaccessible. It was an elegant compromise, but not everyone was convinced. Hawking remained steadfast for decades. He argued that the radiation outside the black hole and the matter inside were fundamentally uncorrelated, that no mechanism could preserve information across the horizon. To him, the mathematics was clear: the universe doesn't always play fair. As the debate intensified, more exotic proposals emerged. Some physicists suggested that the apparent loss of information was an illusion caused by our incomplete understanding of quantum gravity. Others speculated that the radiation might somehow encode the information in an extraordinarily subtle way, so subtle that no observer could ever decode it, but nature itself keeps it intact. In 1997, Susskind and Preskill made a public bet with Hawking and Kip Thorne. If information eventually escapes from a black hole, Susskind and Preskill would win. If it's truly lost, Hawking and Thorne would win. It was a gentleman's wager, but one loaded with existential stakes. Then, in 2004, after nearly 3 decades of defending his position, Stephen Hawking shocked everyone by conceding. At a conference in Dublin, he announced that he had changed his mind. He had found a way, he said, for information to leak out with the radiation after all, though highly scrambled and distorted. In other words, black holes do not destroy information, they only make it unreadable. It was as if the book thrown into the black hole had burned, but the smoke somehow still contained every word, just rearranged into chaos. Hawking presented Preskill with a baseball encyclopedia to settle the bet. Information returned, but in a highly disorganized form. It was the most charming surrender in scientific history. But even that didn't end the debate. The more physicists tried to reconcile quantum mechanics and gravity, the deeper the mystery grew. By the 2010s, new thought experiments began to reveal contradictions in the complementarity idea. If information is stored on the event horizon, then the radiation that escapes should be entangled with that information. But quantum mechanics forbids a single particle from being fully entangled with two separate systems at once. This led to a startling proposal known as the firewall paradox. The firewall argument, introduced in 2012 by Almheri, Marolf, Polchinski, and Sully, suggests that the event horizon might not be smooth at all. Instead, it could be a seething wall of high-energy radiation, a firewall that destroys anything falling in. In this scenario, the graceful fall into a black hole described by general relativity doesn't exist. Anyone crossing the horizon would be vaporized instantly. It was a radical idea because it implied that Einstein's picture of spacetime, smooth and continuous, breaks down completely at the edge of a black hole. The physics community reacted with a mix of fascination and horror. If firewalls exist, they would violate the equivalence principle, one of the cornerstones of general relativity. The idea that locally, gravity and acceleration are indistinguishable. To many, that was unacceptable. To others, it was the price of saving quantum mechanics. The paradox remained: do we protect relativity or unitarity? Do we keep space-time smooth or keep information safe? The universe seemed to demand that one of its pillars must bend. Even now, there is no consensus. Some researchers believe that a deeper theory, perhaps involving quantum entanglement woven into the geometry of space itself, will resolve the contradiction. Others suspect that the concept of a point of no return is more subtle than we ever imagined, and that what we call an event horizon is an approximation, not a fundamental barrier. New mathematical models inspired by string theory and holography suggest that information may indeed leak out in delicate correlations in the Hawking radiation, too faint to detect, but perfectly preserved. And experiments using analog systems such as artificial black holes created in laboratories with sound waves or light have begun to hint that nature never truly forgets. Perhaps that's the lesson in all of this, that mystery is not a flaw in our understanding, but a necessary feature of it. Every time physics seems to close a circle, a new opening appears. Hawking's paradox didn't destroy the unity of science, it deepened it. It forced physicists to confront the limits of their theories and to realize that the universe is more coherent and more enigmatic than we imagined. The information paradox also blurs the boundary between knowledge and philosophy, because at its heart lies a question we've asked in different forms for centuries. Can something truly be lost? Whether it's matter, energy, memory, or meaning. Does disappearance ever mean annihilation or only transformation? In that sense, the black hole becomes a mirror reflecting our own anxiety about oblivion. We too fear being erased, our thoughts, our traces, our identities dissolved into silence. But if the universe itself refuses to forget, perhaps nothing is truly gone. Perhaps everything that ever was still exists somewhere, hidden, encoded, waiting to be rearranged into something new. Stephen Hawking once said, "The universe is not only stranger than we imagine, it is stranger than we can imagine." The information paradox is a perfect example of that strangeness. It is both a scientific puzzle and a philosophical koan. It asks how knowledge survives death, not just of objects, but of space and time themselves. And it leaves us with an image that is at once disturbing and comforting. A black hole evaporating into light, the information of everything it devoured diffusing back into the cosmos, like memory returning to a dream. For centuries, we've imagined the universe as something vast and three-dimensional, a grand stage stretching endlessly in every direction. We picture ourselves moving through space, past stars and galaxies, all suspended within this immense cosmic volume. But what if that volume is an illusion? What if everything we perceive, space, depth, distance, is not the real structure of the universe, but a kind of projection? This isn't philosophy disguised as physics. It's one of the most astonishing scientific ideas ever proposed. And it began, like so many revolutions, with a paradox. When Stephen Hawking discovered that black holes evaporate, he left behind a problem that physics couldn't ignore. If black holes radiate, they must lose mass. And if they disappear entirely, what happens to the information they once contained? Quantum mechanics demands that it cannot vanish. So where does it go? In the 1980s and early 1990s, two physicists, Gerard 't Hooft in the Netherlands and Leonard Susskind in the United States, began to suspect that the answer might lie not inside the black hole, but on its surface. Hawking's own calculations had shown that a black hole's entropy is proportional to the area of its event horizon, not its volume. That was strange enough, but 't Hooft and Susskind took it further. They proposed that this relationship might not be a quirk of black holes at all, but a fundamental truth about the universe. Their reasoning was simple, elegant, and unsettling. If the maximum amount of information a region of space can contain depends on its surface area rather than its volume, then perhaps all of reality is structured that way. Perhaps everything inside, every atom, every star, every thought, is ultimately encoded on a two-dimensional boundary, like an image projected from a screen. In other words, the three-dimensional world we experience might be a hologram. This became known as the holographic principle. And it reshaped the way physicists think about space, time, and information. To grasp what it means, imagine holding a holographic image, the kind you see on a credit card or a piece of art. It looks three-dimensional, yet it's encoded entirely on a flat surface. Tilt it and the image shifts. Move your head and you see new angles. All the depth is an illusion created by interference patterns. The information that builds the 3D image is spread across the 2D film. In the same way, the holographic principle suggests that the information describing everything in a region of space is stored on the surface that encloses it. The world we inhabit might be a projection, not unreal, but a shadow cast by deeper laws. At first this sounded like poetic madness, but physics has a history of turning poetry into equations. Gerard 't Hooft had been exploring the quantum mechanics of gravity, a notoriously difficult field where every attempt to merge Einstein's relativity with quantum theory led to mathematical infinities. Black holes, he realized, offered a clue. If one tried to cram more and more matter into a given volume, the density would increase until it formed a black hole. Beyond that point, no further information could be added without expanding the horizon. The system had a built-in limit, a maximum information density set by the surface area of the horizon. The same must be true, he thought, of any region of space. You can't store unlimited information in a finite volume. Nature imposes a bound, and that bound is geometric. Leonard Susskind took the idea and gave it life. He realized that this wasn't just a curious constraint. It was a new principle of nature. He proposed that the universe itself might obey the same rule as black holes. Just as the event horizon encodes everything that falls within it, perhaps the entire cosmos is a vast holographic surface, encoding the information of everything inside. At first, few took it seriously. The idea seemed too radical, too abstract. How could a universe made of galaxies, atoms, and people be nothing more than information etched on a distant boundary? But gradually, mathematics began to agree. And in 1997, a young Argentine physicist named Juan Maldacena provided the first compelling evidence that the holographic idea might be true. Maldacena's work built a bridge between two very different kinds of physics. On one side was string theory, which describes all particles and forces as tiny vibrating strings moving in higher dimensional space. On the other was quantum field theory, the framework that governs everything from electromagnetism to nuclear physics. Maldacena discovered that in certain cases the two could describe the same system, one using gravity in a curved space, the other using quantum fields on a flat boundary. This correspondence became known as ADS/CFT duality, short for anti-de Sitter space/conformal field theory. It was a mouthful, but its meaning was extraordinary. a complete equivalence between a universe with gravity and one without, between a 3D reality and a 2D description. For the first time, the holographic principle wasn't just a metaphor, it was a calculable theory. You could do math on the flat surface and get results that matched the physics of the volume within. Information wasn't lost or hidden, it was perfectly preserved, just rearranged. In the context of black holes, that meant the paradox could be resolved. Information falling into a black hole could be thought of as encoded on its horizon, not destroyed, just stored in another language. The black hole wasn't a shredder, it was a translator. This realization marked one of the greatest conceptual shifts since Einstein's relativity. The universe, it seemed, might not be a stage where events unfold in space and time, but a network of information woven across boundaries. Reality could be fundamentally digital, not analog, discrete bits of data stitched into the geometry of spacetime. Even gravity, the smooth curvature that Einstein described, might emerge from the entanglement of quantum information. That word, entanglement, is key. In quantum mechanics, entangled particles share a connection so deep that measuring one instantly affects the other, no matter how far apart they are. Physicists began to suspect that the fabric of space-time itself might arise from such entanglements. If you untangled enough quantum information, perhaps space would literally fall apart. In this picture, space-time is not the arena in which physics happens. It is the physics built from the threads of information. The holographic principle didn't just solve a paradox, it redrew the blueprint of existence. There's an almost mystical resonance to that idea, though it's grounded in mathematics. If all that we perceive as volume and depth is actually a projection, then our sense of within and without may be illusions of perspective. Like a hologram, reality might appear three-dimensional because of the way information interferes and overlaps. Every movement we make, every thought we have could be ripples in a vast informational field encoded somewhere beyond our perception. It's a dizzying thought, the kind that makes philosophers sigh and physicists reach for their chalkboards. But this isn't mere speculation. The holographic principle has become one of the guiding ideas in theoretical physics. It underpins much of modern research into quantum gravity, the long-sought unification of Einstein's relativity and quantum mechanics. It offers a framework in which Hawking's radiation, Bekenstein's entropy, and the paradox of information all make sense simultaneously. In the holographic universe, information is never lost. It's simply rearranged across a cosmic screen. Still, the implications reach far beyond mathematics. If reality is holographic, what does that mean for us? For experience, perception, consciousness? Are we projections too? Not illusions, but manifestations of information expressed in higher dimensions? Some physicists avoid these questions, preferring to let philosophy handle them. But others, quietly, admit that the line between physics and metaphysics grows thin at this scale. To understand the universe as holographic is to accept that what we see may not be what truly is. It's worth noting, though, that projection does not mean fake. A hologram is not false, it's simply encoded differently than it appears. The depth we perceive is real to us, even if it arises from a deeper simplicity. In the same way, our universe may genuinely be three-dimensional in our experience, while also being a projection of information on a more fundamental two-dimensional boundary. Reality doesn't lose its meaning, it gains structure. Some thinkers have even speculated that consciousness itself might relate to this holographic nature, that perception is an internal decoding of information patterns from the universe's underlying field. Such ideas remain speculative, but they hint at a poetic unity that mind and cosmos might share the same holographic grammar. In the 1990s, Leonard Susskind summarized it this way: "The world is a hologram." He meant it not as metaphor, but as a literal description of physics. And while we still don't fully understand the mechanism, every new discovery in quantum gravity, from entanglement entropy to the geometry of black holes, seems to echo that same refrain. The holographic principle also changed how physicists think about limits. There's a maximum amount of information, or entropy, that can fit into any region of space, known as the Bekenstein bound. Exceed it, and the system must collapse into a black hole. In a sense, black holes represent the universe's data limit, the point where reality's storage capacity maxes out. Everything we experience happens safely below that threshold, but the principle itself applies everywhere, from atomic scales to galactic ones. It's a reminder that even infinity has rules. Philosophically, the holographic universe blurs our oldest distinctions: inside versus outside, real versus represented, self versus world. If all information is encoded on a boundary, then perhaps we too exist partly on that surface, not as observers standing apart, but as part of the encoding itself. The universe doesn't project to us, it projects through us. It's humbling, but also strangely liberating. Because in such a cosmos, separation becomes illusion. Every particle, every pattern, every heartbeat is connected to every other by the shared code of the boundary. Everything that ever was, is, or will be is written on the same cosmic page. When Hawking radiation first suggested that information might survive, few could have predicted it would lead here, to the idea that space itself is an expression of information. From the event horizon of a single black hole, we arrived at a vision of the entire universe as a horizon. Vast, self-encoding, self-aware. Whether we'll ever prove it experimentally remains uncertain. The mathematics is convincing. The technology is far behind. But perhaps proof is not the point. Perhaps the real significance of the holographic principle is the perspective it offers. That the universe, at every level, is a conversation between what is seen and what is encoded, between image and structure, between being and knowing. It's strange to think that our entire three-dimensional existence might be written on a surface somewhere, a cosmic film shimmering at the edge of reality. Stranger still to realize that even if that's true, it changes nothing about how it feels to be here, to look up at stars, to feel time pass, to wonder about what's real. Projection or not, the universe remains magnificent. Perhaps that's the final beauty of the holographic idea, that it allows the cosmos to be both mathematical and mystical, finite and infinite, surface and depth, all at once. And somewhere, on that vast two-dimensional boundary, the equations describing black holes, radiation, and entropy form a pattern that, when read correctly, becomes the world we live in. Every revolution in physics begins with a contradiction, two truths that both work and yet cannot exist together. At the dawn of the 20th century, those contradictions gave birth to our modern understanding of the universe. Einstein gave us general relativity, the language of the cosmic, the slow bending of space-time under the weight of stars and planets. Planck and Heisenberg gave us quantum mechanics, the language of the microscopic, a restless world of uncertainty, probability, and flickering energy fields. Each theory is a masterpiece on its own. Together, they are enemies that must somehow become allies. For over 100 years, physicists have tried to unite them, to find a single framework that describes all of nature, from galaxies to electrons. That quest has a name, quantum gravity, and black holes are its testing ground. Nowhere else in the universe do Einstein's smooth space-time curves meet quantum theory's jittering uncertainty with such ferocity. At an event horizon, gravity is immense, curvature infinite, and quantum fields swirl in violent fluctuation. It is the ultimate laboratory, though not one any human can enter. And at the heart of it lies Hawking's discovery. Radiation born at the boundary between relativity and quantum mechanics. Hawking radiation isn't just a curiosity. It's a window into the physics that should one day reconcile Einstein and Planck, because it involves both. The geometry of space-time determines where the event horizon sits, that's general relativity. But the radiation arises from fluctuations of quantum fields near that horizon. That's quantum mechanics. The two worlds are intertwined, and yet our equations still treat them separately. The problem is one of scale. General relativity deals with planets, stars, and galaxies, where gravity dominates. Quantum mechanics governs atoms and subatomic particles, where gravity is negligible. But at the Planck scale, about 10 to the negative 35th meters, both become equally important. That's where the fabric of space-time itself begins to quiver, and where our current theories collapse under their own contradictions. At that scale, the very notion of a smooth, continuous spacetime may break down. Einstein's geometry, so elegant on large scales, becomes grainy, a quantum foam of fluctuating curvature, where space and time themselves might appear and vanish like particles in a vacuum. To describe this realm, we need a new language, something that merges Einstein's vision of geometry with the probabilistic grammar of the quantum world. Two of the leading candidates for that language are string theory and loop quantum gravity, different paths toward the same horizon. String theory began in the late 1960s as an attempt to describe the strong nuclear force, but it soon evolved into something far grander, a proposal that all particles and forces arise from tiny vibrating strings of energy, each vibration corresponding to a different particle. Electrons, photons, quarks, all would be musical notes on the same cosmic instrument. Gravity, in this theory, isn't something separate. It emerges naturally as one of the harmonics of those strings. The graviton, the hypothetical quantum of gravity, is simply one mode of vibration. In string theory, space-time isn't fundamental. It's an emergent phenomenon arising from the interplay of these strings. And because strings require consistency in higher dimensions, the universe they describe isn't the familiar four-dimensional one we see. It has 10 or 11 in the case of M theory, a broader framework that unites various string models. Most of those dimensions are thought to be curled up so tightly that we never notice them. To us, they're invisible, compactified realms smaller than atoms, hidden in the mathematical folds of reality. The holographic principle, which grew out of black hole physics, found a natural home in string theory. The famous ADS/CFT correspondence. The idea that a universe with gravity can be equivalent to one without, living on its boundary, came directly from string theory's mathematics. In that sense, Hawking radiation, entropy, and holography all became pieces of a much larger puzzle, the unification of the quantum and the gravitational. But string theory, for all its beauty, remains largely theoretical. It's elegant, self-consistent, and extraordinarily difficult to test. Its scales are far beyond anything we can probe with current experiments. Critics sometimes joke that string theorists have replaced physics with metaphysics, that their universe, though mathematically exquisite, might never meet the real one. The other great contender, loop quantum gravity, takes a different route. Where string theory adds dimensions and complexity, loop quantum gravity simplifies. It starts directly from Einstein's equations and tries to quantize space-time itself without invoking extra ingredients. In this approach, space is not continuous, but made of discrete loops, tiny finite structures that weave together to form the fabric of the cosmos. Think of it as a cosmic chainmail, each link representing a quantum of area or volume. At the smallest scales, space becomes granular. Distances, areas, and volumes are not infinitely divisible. They come in indivisible units, like pixels on a screen. Time, too, might tick in discrete moments, like the frames of a film. In loop quantum gravity, singularities, those infinite points inside black holes, never actually form. They are replaced by finite regions where the density and curvature of spacetime reach a maximum and then bounce back. If true, it means that black holes may not end in infinite compression, but in transformation, perhaps even rebirth. Both theories, strings and loops, approach the same mystery from different sides. One starts with quantum fields and tries to make gravity emerge. The other starts with gravity and tries to make it quantum. Neither is complete, but both have illuminated new paths toward understanding Hawking's paradox. In string theory, Hawking radiation fits naturally into the holographic framework. Information isn't lost. It's encoded on the horizon and radiated back out in subtle correlations. In loop quantum gravity, the granularity of space may prevent true information loss by replacing the singularity with a bounce, preserving data in a new phase of spacetime. Both suggest that the ultimate theory of quantum gravity will make information preservation not just possible, but inevitable. The challenge, however, is evidence. We can't create black holes in laboratories. Not yet, at least not astronomical ones. But physicists are creative, and they found ways to simulate them. In 1981, William Unruh, a Canadian physicist, proposed that black hole horizons could be imitated using sound. If a fluid flows faster than the speed of sound, then sound waves within it can't travel upstream, just like light can't escape a black hole. This creates a kind of acoustic horizon, and if Hawking's mechanism is universal, if it truly arises from the physics of horizons and not just gravity, then these sonic black holes should also emit radiation. Not photons, but phonons, tiny quantum vibrations in the fluid. It sounded fanciful, but in recent years, experiments have confirmed it. In 2010, physicist Jeff Steinhauer at the Technion in Israel created an artificial black hole using a cloud of ultra-cold rubidium atoms, a Bose-Einstein condensate. He accelerated part of the fluid to supersonic speeds, forming a horizon for sound waves. Then he detected pairs of correlated phonons on opposite sides of that horizon, one falling in, one escaping, just as Hawking's theory predicted. It was not a perfect black hole, of course, but it showed that the physics of horizons transcends gravity. Wherever you have a boundary that separates two regions, one where signals can escape, one where they cannot, you can have Hawking-like radiation. These analog systems, sonic black holes, optical horizons in lasers, even event horizon-like behavior in superconducting circuits, allow us to probe the untestable. They're models, not literal black holes, but they reproduce the mathematics of the real thing. They let us watch in slow motion and in human timescales what the universe does on scales of 10 to the power of 66 years. And they remind us that Hawking's insight was not about exotic astrophysical objects, but about the nature of reality itself. It's about how boundaries, in space, in knowledge, in theory, generate phenomena that seem to transcend them. These experiments mark a turning point. For decades, the study of black holes was purely theoretical, a playground of equations, chalk dust, and thought experiments. Now, for the first time, we can test some of those ideas, even if indirectly, and every successful analogue reinforces the belief that the physics of black holes, their radiation, their entropy, their information, is universal. It doesn't belong only to distant galaxies. It belongs to the deep structure of reality. Still, the ultimate prize remains elusive, a true, experimentally verified theory of quantum gravity, one that unites the continuous and the discrete, the smooth and the granular, the deterministic and the probabilistic. It's a theory that would explain not only how black holes evaporate, but how the universe began, and perhaps how it will end. Hawking radiation remains our beacon on that path. It's one of the few phenomena that sit squarely at the intersection of general relativity, quantum field theory, and thermodynamics. Whatever theory finally unifies those pillars will have to explain it. Not just approximate it, but derive it naturally, elegantly, inevitably. Perhaps that's why black holes have become the philosopher's stones of physics. They transform whatever touches them, matter, light, information, ideas, and reveal what survives the fire. They expose the contradictions that keep us honest, and the mysteries that keep us searching. And they remind us that the boundary between theory and experiment, like the event horizon itself, is not a wall but a bridge, one that we're still crossing, one discovery at a time. Somewhere, beyond our laboratories, real black holes are evaporating at their imperceptible pace, losing mass one quantum at a time. And in cold rooms filled with lasers and magnetic traps, their tiny artificial counterparts are doing the same. Between them lies the continuum of understanding, from the mathematical to the tangible, from the infinite to the microscopic. Perhaps one day the two will meet. Perhaps the final theory of quantum gravity will emerge not from equations alone, but from the quiet hiss of phonons in a lab, or the faint echo of a Hawking photon escaping from a dying star. And when that day comes, we may finally see that Einstein and Planck were never truly at odds. They were describing the same universe, just from different sides of the horizon. Until then, the search continues. At the edge of knowledge, where space becomes granular and time uncertain, physics still listens for the faint sound of understanding rising from the void, the soft, persistent whisper that Stephen Hawking first heard half a century ago. Stephen Hawking's story was never just about physics. It was about defiance against time, against fate, against the limits of the human body. Born in Oxford in 1942, exactly 300 years after the death of Galileo, he entered a world still recovering from war and quietly set out to understand the universe that had nearly destroyed itself. He wasn't an exceptional student at first. He once joked that his classmates called him Einstein mostly as a tease. But there was something in the way he thought, a stubborn curiosity that refused to take limits seriously. That refusal would become his defining trait. At the age of 21, while studying at Cambridge, Hawking was diagnosed with amyotrophic lateral sclerosis, ALS, or motor neuron disease. The doctors gave him 2 years to live. The neurons that controlled his muscles were dying. The rest of him, they said, would follow. He fell into despair, stopped working, stopped planning for a future that he no longer believed existed. But then, life, quiet and improbable, began again. He met Jane Wilde, who would later become his wife. He returned to his equations, and when he realized that his disease was progressing far more slowly than predicted, he made a decision. If he could not walk, he would think. If he could not speak, he would write. If he could not move through space, he would explore time. The disease continued its merciless work, taking his voice, his hands, his independence, but it never took his imagination. In fact, many of his students and colleagues said that as his body weakened, his clarity deepened. As if, freed from the distractions of motion, his mind could focus entirely on the abstract. He spoke through a computer voice synthesizer, one slow word at a time, but his thoughts travelled faster than light. In 1975, he published the paper that would redefine emptiness. It appeared in Communications in Mathematical Physics under the modest title Particle Creation by Black Holes. In it, he demonstrated that black holes, once thought to be eternal prisons, must emit radiation, that the vacuum itself, when curved by gravity, becomes a source of light. From that moment on, nothingness would never again be truly nothing. He had shown that the universe hums, even in silence. That paper did more than introduce Hawking radiation. It bridged the greatest gap in science, the one between Einstein's smooth cosmos and the jittering chaos of the quantum world. It was a synthesis that even Einstein himself had never achieved. Hawking had done it with a single devastating calculation, performed by a man who could no longer hold a pen. The discovery made him famous, but his fame was unusual. It wasn't just the brilliance of his ideas, it was the contrast between his frail body and the immensity of his thoughts. He became a symbol of the mind's endurance, proof that intellect and curiosity could survive even as the body failed. Through his synthetic voice, he spoke with humour, wit, and a kind of cosmic irony. "I have lived with the prospect of an early death for the last 50 years, he once said, but I'm not afraid of dying. I'm in no hurry to die. I have so much I want to do first." He did. He wrote A Brief History of Time in 1988, dictating it slowly, letter by letter. It sold more than 10 million copies and brought cosmology into living rooms, classrooms, and bedside tables around the world. Millions of people who would never read a physics paper came to feel that they too could ask what happens at the edge of a black hole or at the beginning of time. He made the universe feel intimate. Among physicists, he remained both revered and challenged. Leonard Susskind, one of his fiercest scientific opponents, later called him the single most stubborn person I have ever met, and also the one I respected most. Their debates over the information paradox stretched for decades. In the end, when Hawking conceded that information might escape after all, Susskind said it was the greatest act of intellectual humility I've ever witnessed. Roger Penrose, his one-time mentor and collaborator, admired Hawking's courage in both science and life. Together they had proven theorems showing that singularities, the points of infinite density in black holes, are not exceptions, but necessities. Later, Penrose would say that Hawking's brilliance lay not only in his mathematics, but in his imagination. He could see through the equations, beyond them, into what they really meant. Kip Thorne, the American relativist who worked on the film Interstellar, called Hawking the most audacious physicist since Einstein. Audacious because he didn't just solve problems, he invented them, paradoxes that forced the rest of physics to grow around them. The information paradox, the thermodynamics of black holes, the holographic principle, all of these arose because Hawking asked questions that others thought impossible. In the decades that followed, his ideas grew beyond him. The equations he wrote on the nature of radiation inspired fields he never lived to see mature. Quantum gravity, holography, and the study of entanglement entropy. Each is, in some way, an echo of that 1975 paper. The moment the universe's most silent objects were found to have a voice. Yet for all his genius, what most people remember is not the equations, but the courage. The sight of him, seated, immobile, yet smiling, joking, lecturing, arguing, was a lesson in persistence. He once quipped that life would be tragic if it weren't funny. It was that dry humour that kept him, and those around him, sane. He loved paradoxes in physics, but he also lived one, a body in decline, a mind ascending. When he died in 2018 at the age of 76, his ashes were interred at Westminster Abbey between the graves of Isaac Newton and Charles Darwin. It was a fitting trinity, the laws of motion, the laws of life, and the laws of the universe, side by side. As his funeral procession passed through Cambridge, students lined the streets in silence, some clapping, some crying, some just standing in awe that such a fragile human being could have reshaped the cosmos. Hawking once said that the greatest enemy of knowledge is not ignorance, but the illusion of knowledge. He never stopped doubting, never stopped questioning, never stopped laughing at the seriousness of it all. His mind was both a scalpel and a mirror, cutting through illusion while reflecting the strange beauty of existence. Perhaps that's his true legacy. Not just that he showed us how black holes evaporate, but that he showed us how to live, how to confront the inevitable with curiosity instead of fear, and how to look at the vastness of space and feel not small, but connected. The last line of A Brief History of Time reads, "If we find the answer to why the universe exists, it would be the ultimate triumph of human reason, for then we would know the mind of God." Whether or not that answer is ever found, Stephen Hawking brought us closer to it, one whisper of radiation at a time. Imagine time stretched beyond imagination, beyond years, beyond centuries, beyond even the lifetimes of galaxies. Try to picture a clock whose hands tick once every billion trillion years, and then stop picturing it, because even that clock would be too impatient for what comes next. The story of the universe is a story of cooling, from the white heat of the Big Bang to the dim glow of the cosmic background, to the quiet embers of dying stars. Entropy increases, energy spreads, every bright thing burns and fades, until the cosmos itself begins to rest. In the far future, long after the last star has shone its final light, the night sky will be black again. The galaxies we see today will have drifted so far apart that their light will no longer reach one another. Space will expand faster than photons can travel. Every island of matter will become isolated, sealed within its own bubble of darkness. Stars will exhaust their fuel, collapse, or freeze. Planets will wander alone through intergalactic space, their orbits meaningless without suns to circle. This is the beginning of what cosmologists call the degenerate era, a time when the universe is no longer ruled by starlight, but by the faint, slow decay of remnants. White dwarfs will cool into black dwarfs, cold spheres of carbon and iron no warmer than the background around them. Neutron stars will drift like frozen relics of gravity. Occasionally, by chance or collision, a few might spark a brief flare, a momentary rebellion against silence. But even those will end. Then come the black holes. They will dominate the universe long after everything else is gone. Each one, vast and patient, will sit in the void like a silent monument to what once was. Galactic cores, stellar corpses, primordial holes, all slowly leaking their mass through Hawking radiation. It is a process so slow it defies language. A solar mass black hole will take about 10 to the power of 66 years to evaporate. A supermassive one, the kind found in the hearts of galaxies, could last 10 to the power of 100 years or more. Trillions upon trillions upon trillions of ages will pass before they even begin to dim. By then, even protons may have decayed, dissolving matter itself into light and neutrinos. Gravity will have no structures left to bind. The universe will consist mostly of black holes, radiation, and emptiness, and even those black holes will be shrinking pixel by pixel, quantum by quantum, until at last, one by one, they vanish. The final moments will be beautiful in a way that only mathematics can describe. As a black hole's mass dwindles, its temperature climbs. The colder it once was, the hotter it becomes at the end. The process accelerates. Centuries compress into seconds. In a final burst, it radiates all that remains in a blinding flash of gamma rays, like a single note rising from an orchestra that has been fading for eons. Then it's gone, a whisper of light dissolving into silence. If we could watch from some eternal vantage, we would see the last of them. Perhaps a primordial black hole, no larger than a mountain, glowing blue-white in the dark. It would release its final photons and vanish, leaving behind no trace, no shadow, only the afterglow of its departure. And then the universe would fall completely still. What remains after that is not darkness, because darkness requires contrast. It is not cold, because cold requires the memory of warmth. It is something quieter than both, a perfect equilibrium where nothing changes because nothing can. This is heat death, the ultimate expression of the second law of thermodynamics. Entropy has reached its maximum. All gradients of temperature, pressure, and potential have flattened into sameness. Every possible transformation has already occurred. There is no motion, no time in any meaningful sense, only a uniform sea of low-energy photons expanding forever into a space too vast to measure. To human minds, this sounds like an ending. And perhaps it is, but it can also be seen as a kind of completion. The universe began in violent asymmetry, high energy, concentrated in one small point. Every explosion, every star, every life has been part of its journey toward balance. In the end, the universe doesn't die. It finishes its sentence. Some physicists have imagined other fates. A big crunch, a big rip, a bounce that starts the cycle anew. But in each scenario, the same principle lingers. Entropy wins. Whether through collapse or dispersal, order dissolves into potential. The arrow of time stretches forward until it no longer needs to. And yet, there's something strangely peaceful about this vision. When even gravity forgets itself, when the last black hole fades into transparency, the universe will finally be free of tension. No forces pulling, no masses resisting, no light chasing darkness, just equilibrium, unbroken and infinite. If the cosmos had a consciousness, perhaps it would see this not as death, but as rest. A return to the stillness it left behind when it exploded into being. Every atom, every photon, every thought that ever existed will have played its part in bringing it there. The universe, having explored all its possibilities, will close its eyes, and perhaps, in that silence, something eternal will remain. Not matter, not energy, but the symmetry of it all, the beauty of balance, the echo of everything that ever was, suspended in the perfect calm that follows creation. The final whisper of evaporation will not be a scream or a bang, but something softer, the sound of completion, a universe cooling into its own reflection, serene, fulfilled, and at peace. Nothing. It's a word we use easily, yet never fully understand. We say, there's nothing there, but even emptiness hums with the quiet vibration of existence. Virtual particles, faint radiation, the background memory of creation itself. The universe has never truly known silence. Even its final breath, the fading of the last black hole, will be a whisper, not of death, but of completion. Stephen Hawking once said that the universe doesn't allow perfection. Entropy ensures that everything changes, that order must eventually yield, and yet, in that surrender lies a kind of grace. A universe that fades is a universe that has lived. Its death is not tragedy but transformation. The moment when all movement, all difference dissolves into peace. We tend to think of decay as loss, a dying star, a collapsing life, a vanishing world. Each feels like subtraction. But in truth, decay is the way the universe recycles meaning. Nothing is ever truly gone, it only changes form. Atoms that once made up the heart of a star become the minerals of a world, the cells of a living being, the breath of someone watching those same stars. Entropy doesn't erase, it translates. Perhaps the end of the universe, that cold, still equilibrium, is not the negation of existence, but its fulfillment. The moment when everything that could happen has. Every dance of energy, every flicker of light, every story written and forgotten. It's the symmetry after the storm, a cosmic exhale that has been waiting for trillions upon trillions of years. There's something almost human in that pattern. We too resist endings. We too fear the quiet that follows. But maybe the lesson of Hawking's universe is that endings are not failures. They are continuations written in another language. Even in death, there is information. Even in nothing, there is structure. Hawking's radiation reminds us that the void itself can speak, that silence is not empty, but full of potential. It's easy to think of black holes as symbols of destruction, but they are also symbols of persistence. They take everything in, and yet, at their edge, they give something back. A soft light, a quiet reminder that the universe always balances its books. When we stare into the night sky, we're not looking into darkness, we're looking into memory. Every photon, every faint shimmer of starlight is a story billions of years old. Even after the stars are gone, their echoes will travel, a soft radiance moving outward forever. Perhaps that is what beauty truly is. Not perfection, but endurance. Not the absence of change, but the grace to exist within it. And so when we speak of the end, of black holes, of time, of everything, we're really speaking of transformation, of how the universe keeps finding ways to express itself, even in silence, of how we, made from the dust of ancient stars, are temporary forms in a long conversation between order and chaos. We rise, we burn, we fade, but we belong to something larger that never truly ends. The philosopher might call it impermanence, the physicist might call it entropy. But perhaps they are the same thing, the universe learning how to let go. So, as this exploration draws to a close, take a breath. Think of the vastness of everything that has ever been, and how, somehow, you are part of it, made from the ashes of old stars, living on a world that floats between creation and decay, thinking thoughts born from the same laws that govern galaxies. In that sense, you are the universe, briefly aware of itself, and that awareness, fleeting as it is, might be the most beautiful thing it ever produced. Thank you for listening, for thinking, for drifting through the dark with curiosity. If you enjoyed this quiet journey, consider leaving a comment. Tell me where in the world you're listening from and what time it is there. And if you'd like to keep exploring these calm corners of science and wonder, you can subscribe to the channel so you never miss the next story the universe wants to tell. Until then, may your nights be quiet, your thoughts slow, and your imagination infinite. Good night.